Good morning, students. I hope you're all well. I developed a little cough, and so it's enough to make me nervous to come to class in case it's the bad stuff. I don't know for sure. It might just be a little cold. I get a little cold every year, and I haven't had one yet this year, so maybe this is it. So I should be able to, to figure that out by next week. So I'm just going to record today's lesson for you, the lecture, and you should be able to follow along and fill out what's in the book. Okay, so here we go. We're on Module 15, Lab 31 and 32, and we're going to be looking at something called equilibrium. All right, so you're going to find out that stuff I've told you all this year is a little wrong. And that is, we aren't necessarily always making nothing but products. Let's watch the introduction.
Say two people are walking down the street and they bump into each other. They'll just shake it off and walk on. Sometimes that happens with molecules too. They just bounce off each other and that's that. But what if two people were to bump into each other and during that collision, one person's arm got severed and reattached to the other person's face? Now that sounds really weird, but it's similar to one of the many ways that molecules can react with each other. Two molecules can join and become one. One can split apart and become two. Molecules can switch parts. All these changes are chemical reactions, and we can see them happening around us. For example, when fireworks explode, or iron rusts, or milk goes bad, or people are born, grow old, die, and then decompose. But chemical reactions don't just happen willy-nilly. Everything has to be right. First, the molecules have to hit each other in the right orientation. And second, they have to hit each other hard enough, in other words, with enough energy. Now you're probably thinking that a reaction just happens in one direction and that's it. Sometimes that's true. For example, things can't unburn or unexplode. But most reactions can happen in both directions, forward and reverse. There's no reason that our face arm guy can't bump into armless girl, reattaching that arm back to its original socket. Now let's zoom out a bit. Now let's say that you've got 1,000 people on the street, and all of them start with their limbs normally attached. At the beginning, every collision is a chance for person A to transfer an arm to person B's face. And so at the beginning, more and more people end up with arms attached to their faces or arms missing. But as the number of people with arm faces and missing arms grows, collisions between those people become more likely. And when they bump into each other, guess what? Normal appendage people are reproduced. Now the number of limb transfers per second forward will start high and then fall. And the number of limb transfers per second backward will start at 0 and then rise. Eventually they'll meet, they'll be the same. And when that happens, the number of people in each state stops changing, even though people are still bumping into each other and exchanging limbs. Now, how many people do you think there are in each state? Half and half, right? No, well, maybe. It depends. It could be 50-50, but it could be 60-40 or 15-85 or anything. We chemists have to get our little gloved hands dirty. Well, we're in a lab, so not really dirty, to figure out what the actual distribution of molecules is. Even though each of these limb transfers is a pretty dramatic event for the people involved, if we zoom out, we see population numbers that don't change. We call this nirvana equilibrium, and it doesn't just happen with chemical reactions. Things like gene pools and highway traffic show the same pattern. It looks pretty still from 30,000 feet, but there is lots of crazy stuff happening on the ground. You just need to zoom in to see it.
All right, so that's kind of a strange video, but it's very accurate the way it was saying that. So it turns out that, look at the bottom here, we have a reaction, AB plus C will yield AC plus B. And that little arrow, that double arrow thing in the middle shows that it's actually going both ways. And what happens is these will meet up in a place called equilibrium. All right, so that just as many are going to be forming products as forming reactants. So a point at which the forward and reverse reactions in a chemical equation have equal reaction rates is called equilibrium. All right, so when that happens, the amount of these substances in the chemical reaction don't change at all. They're changing a lot, but then in general they don't change because they're staying at this equilibrium status. So I think you're supposed to probably write that one down. If I go, by the way, too fast on this, you can always pause the video and write down what you need. Okay, so I'm going to move on. All right, so if we have a reaction that is, its equilibrium is that more products are formed, we call that a reaction going forward. And then if we have one that not as many products are being formed, it's not a very good reaction, then we have it going backward. The reaction's going backward. If they're in equilibrium, which every one of them is going to have that at some point, we're going to see how we can manipulate that. We have those arrows equal right there. So sometimes I'll show the two arrows going back and forth. Sometimes I'll just show one line with an arrowhead on each side. It just makes it a little more, it's a little easier in my computer program. Okay, so like the video showed, we have the forward reaction starts here with lots and lots of reactants coming down and making products. I start with 0 products and I go up, and as it gets done like this, goes up and up and up, I'm making more and more products. So here I have that equilibrium state. In this particular reaction, the equilibrium state happens at this time, whatever it is, and we can see equilibrium take place. So now the question is, if I'm trying to make HI, hydrogen iodide, how can I make that happen without it going into equilibrium? In other words, I'm trying to make something here. So if I try to make something, then I can maybe manipulate it to make more product, you see. So I can get it to shift over. The equilibrium can shift over. You know, for instance, if I add a heat or something like this to it, I can get that that forward reaction to be more dominant, and therefore I end up with more product. And that's kind of what chemistry is all about. Okay, so notice in beaker 1, I have A plus B, so I have 2 different colored dots in there. The reaction begins. There's no products yet because it just started. And there's a high rate of collision between A and B, so it's going to be moving forward. And as we get to 2 and 3, you see how they're starting to get more of the C and D product made, and therefore the collisions are going to decrease between the reactants, and the rate of the forward reaction will decrease. And some reverse reaction will begin. So notice the long blue arrow and the short red arrow. Okay, and then in beaker number 4, the rate of forward reaction is equal to the rate of reverse reaction. We're reaching right here something known as dynamic equilibrium. The reason it's called dynamic is because it's always moving. It's not static, okay? So dynamic means moving. So we're making A and B and we're making C and D. We're making, though, at the same rate. Therefore, we call that equilibrium. Okay. So the concentrations, I like that. The concentrations are constant right there. Okay, remember if we have gases that we're talking about here, in order for this to be true, we have to run them in a closed system. And this is because if I don't run it in a closed system, guess what's going to happen with those gases? Think about your volcano, right? You've got your baking soda, you've got your vinegar, and the gases, the bubbles, just float off into the air, yeah? So if I'm not keeping those contained, then I will not reach equilibrium there. All right, in other words, that'll be like this limiting product, right, that floats off into the air, so I'll be making more and more of my product. All right, there is an interesting lab in the book, and it looks something like this. You have these bottles and they flow out. It's I don't usually do it in lab time because it's a little messy for one, but read through it and see how it's just a demonstration. It's not actually doing anything except showing you an idea of what equilibrium would look like. Yeah, so that's experiment 15.1. Take a look at that. Okay, now in order to figure out how to measure this equilibrium, when does a reaction get into equilibrium? Can I do something about it once it's there? You know, what would it do? How can I do chemistry with that? Well, we're going to use something known as the equilibrium constant. So the equilibrium constant is K, a large letter K right there. And we do that by taking our equation, A plus B equals C plus D. The little letters in front of them are the stoichiometric coefficients. All right, so that's kind of nice, right? So we can use our stoichiometric coefficients again. So how we're going to do this, how we're going to calculate K, is to take the concentration of the products, so C and D, raised to the power of their stoichiometric coefficient. So the last time we were talking something like this, the coefficient didn't have anything to do with it, but this time it does. So this is our friend here. We really like our stoichiometry in this lab. Okay, so C times D, each raised to their coefficient, over A and B times B raised to their coefficient. And we'll be able to calculate then a equilibrium constant called K. And once we calculate that, we can know some things about these reactions and make predictions about these reactions. Okay, so the equilibrium constant is the relationship between the products and reactants raised to their stoichiometric coefficients. This is what you're going to write down in your book. Okay, and you're going to either write down that K right there or it's already written for you. I'm not sure. Okay, let's try an example here. All right, the following reaction has reached equilibrium when N2 is at 0.354 molar, O2 is at 0.124 molar, and NO is at 4.51 molar. All right, notice my little arrow going back and forth between those. So what's the equilibrium constant? Oh, I will also tell you in this particular case, in this module, our state, gas, liquid, aqueous, solid, these are important. So we're going to need those in their little parentheses right there. They're going to be important. You'll see why in a minute. Okay, so I'm going to take my K. I put my products raised to the coefficient. I drew that arrow there for you. And over the concentration of N2 and the concentration of O2. And that EQ just means they're at equilibrium. So for the rest of the examples today, I'll probably leave the EQ out of there because it just takes up so much room. Maybe we'll see it again, I'm not sure. Okay, so I plug my numbers in, and what do I get for K? I get 463. Now, this particular answer ends up with no units, and that is strange. All right, so we have a unitless answer. So the answer is just 463. Just 463, that's it. That's the equilibrium constant for this reaction at that temperature. They didn't tell us the temperature, doesn't matter at this point, but temperature would make a difference. But at this temperature, let's just say standard temperature, this reaction will go with a K of 463, which is a pretty big number. And we're going to find out in a minute what that means for it to be a big number. Okay, what is the value of K for the following reaction if N2 is at 0.121 molar, H2 is at 0.234 molar, and NH3 is at 1.14 molar? Okay, here's our reaction. N2 and H2 gives me 2 NH3. Now check out the states. They're all gases, so that's good. So we're going to take our products, put it on top, and our reactants and put them on the bottom, raised to their coefficients. You see those coefficients, the 2 and the 3. And my equilibrium EQ is in here again. All right, I plug the numbers in, and we get the answer of 838, 1 over molar squared. So here we do have units. It's not dimensionless on this particular one. So kind of like in Module 14, sometimes those units will change based on whatever reaction is going on. All right, so yeah. So just try a couple of those practice ones like that. They're not too bad, especially if all we're asking for is K. It's just simple math right there. Okay, if a chemist starts with 1.30 molar SO3 and no SO2 or O2 because they haven't been made yet, he finds that the reaction reaches equilibrium when SO3 reaches 0.20 molar. At that point, SO2 is at 1.10 molar and O2 is at 0.55 molar. So what is K? This is, once again, a simple question. I don't know if this is one of the on your owns or not. I'm not sure. So we're going to see our products over our reactants raised to their stoichiometric coefficients. We'll plug our numbers in, and our K is going to end up equaling 17. Now notice that's a much smaller number there. All right, so we're going to see in a minute how that K, the size of it, makes a difference. Okay, so what does it tell us? The equilibrium constant, K, tells you what the concentration is of reactants and products at equilibrium. It can be used as a gauge, though, also to predict chemical reactions. Can they go? Remember how we had to answer questions when it came to thermodynamics? Is a reaction going to go? Does it meet its thermodynamic criteria? We're going to have that same thing here. If it has a high K or a low K, we're going to see how that's going to result in a successful formation of products or not so successful. Let's see, it also tells you if it's actually at equilibrium. It doesn't change. As long as the temperature doesn't change, it'll be the same. In fact, we could have a chart somewhere that said for any reaction, and you have on the chart at such and such temperature, the K will equal this, and it'll be the same every time. It doesn't change, as long as the temperature stays the same. Okay, so when you calculate K, this is just a kind of a little hint here for you. So let's say we've just calculated K, and if it's large, like a couple of those first ones, there will be more products at equilibrium than reactants. So it's weighted toward the products. Okay, so you get it? It's got a large K. Therefore, I will be successful in making lots of products, which I assume is our goal here. Next, if my K is small, then there will be more reactants at equilibrium than products. So it's weighted toward the reactants. So you think, well, why would I want to do that one? Well, what if I'm trying to make something, and even though my products will be small, and at equilibrium, once they get to equilibrium, I won't have very many products at all. Maybe I can do something to manipulate it to get more and more products. All right. If K is close to the number 1, then the reaction is pretty much balanced, kind of like the video said, 50-50. It's kind of like that. Between reactants and products. But when K is very large, there's virtually no reactants left, and we can say it's gone completely to, making all of those products. Okay, so I think that first example we did had a very large K, and that would be successful to make all of those products and leave no reactants behind. Okay, but keep in mind that there's still a equilibria going there. It's just in that particular reaction, it tends to go toward products. Okay, so restating it. If my K has my product over reactant, and the product has a large number and the reactant has a small number, we get a large value for K. So we use the arrow going to the right. We make lots of products. If my product over reactant is a small number over a large number when I do my math, then the small value for K, so we use our arrow going toward the reactants. If my product over my reactant equals very close to 1, then we'll use that double arrow thing right there. Okay, and sometimes I just use an arrow on each end of it. So that's just restating it, if that helps at all. There are some restrictions. So this is coming to the idea about what state are these things in. So if there's a solid that appears in a chemical equilibrium, we just don't even pay attention to it. I mean, you just ignore it. So it's kind of like a 1, which I love that when it comes to math. Y'all know that. And so the reason this is because once it becomes a solid, it tends to stay very close to itself, right? And therefore, it's not going to be doing a lot of colliding and things like that. Okay, and then furthermore, if there's a liquid that appears in the chemical equation, we do not include that in K either. And it also has to do with it stays to itself and doesn't react with the stuff that's in the gas form or whatever. So, but always consider gases and aqueous. So don't be fooled. Liquid and aqueous are not the same thing, remember. A liquid is when it actually is in a liquid state. Aqueous is when it's mixed with water. Remember that? So always consider G gases and AQ aqueous. So, for instance, if we have H2O2, which we did this, remember, we did this last week. We took our hydrogen peroxide and we wanted to make H2O and O2, and it was very, very slow. So we added something to it. We added potassium iodide. I also did the beaker that we added the yeast to it. Remember, the yeast was acting like a catalyst. And then we did the reaction with the Ki and made that elephant's toothpaste stuff. And we did the different concentrations. Okay. All right, so we're going to have our K is going to disregard the H2O because it's a liquid. But our O2 will go over our H2O2 raised to the second power, which is the stoichiometric coefficient. Notice H2O is just completely ignored. I don't care about its stoichiometric coefficient. I don't care about it. I'm just going to calculate based on O2 and H2O2. All right? Easy breezy. So, what is the equation used to calculate K in the following reaction? look what I have on my, this is interesting because my reactants are a solid, and the solid is apparently just going to just dissociate into NH3 and HCl gases. So my K, I'm just to ignore my solid completely, my K will only take into account products. So that's kind of a strange one. All right, that's example 15.2. If you're supposed to write that down, remember you can pause this if I'm going too fast. All right, so let's take a look at this one. We have lithium and H2O is going to be making lithium hydroxide and have some hydrogen left over as a gas. So what am I not going to consider? I'm not going to worry about the solid or the liquid H2O. I'm just, once again, going to worry about my products. So I put my LiOH to the 2 right there because of its stoichiometric coefficient, and my H2, and that's all I have to do for my K. So not bad, huh? Not bad at all. All right, so the review is that the rate forward is equal to the rate reverse. Sometimes those arrows are, more weighted to one side than the other, but yet still at equilibrium. And it has to occur in a closed system. That's because since we're dealing with gases, remember what I said? We had to keep those gases from floating off into space. One of our ways of actually manipulating would be to let it, float off into space, and that will manipulate our reaction. Okay, so now we're in 15b. Okay, so this was review. So turn your pages over to 15b, and we're going to now use our K to predict equilibrium, and then we're going to look at how we can change it. So K can be used to predict whether or not a chemical reaction has actually reached equilibrium. This is restating a little bit because we're in part B. If you know K for a certain reaction at a particular temperature, you can use that information to tell if the reaction is at equilibrium. So plugging in the concentration numbers at any point and comparing it to K will allow you to predict what will happen next. Okay, so this will be more clear when we do a little example right here. Okay, so a chemist is studying the following reaction. N2 plus O2 gives me NO. Oops, I didn't tell you what NO was. I'm guessing it's a gas. Okay, sorry about that. She knows that the equilibrium constant is 0.050 K at this particular temperature. Suppose she knows that the concentrations of each substance at this moment in time are N2 at 1.5 molar, O2 at 1.3 molar, and NO at 0.020 molar. So now the question is, has it reached equilibrium? If not, what will it do? All right, so all we have to do is take those numbers, plug them in, and see how close they come to that 0.50, which is the K that we know at this particular temperature. All right, so consider this. Here it is. All the numbers are up there that you need. So I'm going to take my, oh look, my NO has the gas. Good, yay. I'm going to take my numbers and I'm going to plug them into K, and when I do the math, when I come through the math, I find out that it's 0.00021, but we know that the equilibrium constant is at 0.050. So this reaction has not reached equilibrium. It's a very small number, so it's going to shift toward the products because 0.00021 is less than 0.50. Okay, so it'll shift. It's still going. It's still proceeding in its chemical reaction. All right, so you may have some questions like that. That's the example in your book, and there's probably some OIOs as well. All right, part 2. The same chemist studied the same reaction under different concentrations. Okay, so we're going to have a different concentration now. We can see up at the top we have our N2, our O2, our 2NO, and our K equals 0.050. So we're at the same temperature, but we have different concentrations. All right, so we're going to have N2 at 0.100, O2 at 0.200, and NO at 1.00 m. So is the reaction at equilibrium? If not, how will it shift to reach it? I put all the numbers in, and I end up with 50. Yikes, it's huge. The reaction is not at equilibrium. The calculation is larger, so things must shift to decrease that number. So if the value of NO is decreased, that's in the numerator, it will decrease the value. So therefore, the reaction must shift to the reactant. So the arrow will be going back to the left, okay, toward the reactants. All right, so we're just comparing those numbers right there. That's all we're doing. It's not difficult. I don't mind the math in this one so much. All right, this is a picture of Henri Le Chatelier. And so he's a Frenchman, And we don't write this down just yet. His principle, it's going to be very, very similar to this, but I'll have the words a little more clear for you. It's just he just noticed that we can manipulate that equilibrium. We can manipulate the way that the reaction will proceed if we do something to it. Okay, we stress it out. So Chatelier says we're going to stress out the system. So here's what I want you to write down. When a stress, which includes a change in concentration, a change in pressure, or a change in temperature, is applied to an equilibrium, the reaction will shift in such a way to relieve that stress and restore equilibrium. So these reactions want to be at equilibrium. That's the goal. And because of that, a stress will change what happens. So we call him Le Chat, because Le Chatelier is hard to say. So Le Chat, it's interesting, that means the cat, but it ignores solids and liquids, similar to K. If we add pressure, so we need to remember this, y'all. You may want to write down this little note in your book somewhere. If we add pressure, the reaction shifts away from the most gases. So wherever the more gases are on which side of the reaction, it'll shift away from that. If I decrease pressure, the reaction will shift toward the gases wherever they are. So let's look at an example. Here we can see that, first of all, this is just a general deal. If I've reached a state of equilibrium and then I do something, so that arrow here that says equilibrium disturbed by changing the concentration of PCl5, it looks like, then that bumps it up again, it stresses it, and then it does something, that little graph coming down there, to get back to a state of equilibrium. All right, so this is just kind of showing you in a graph form. All right, let's watch a little video, see if this will help us.
In this lesson, you will learn about Le Chatelier's principle, which explains what a system at equilibrium does in response to stresses. Let's return to our original example of you digging a hole and your friend refilling it simultaneously. If you start digging at a rate faster than refilling, the hole gets larger. In order to maintain a constant size of the hole, your friend must work harder to fill it faster. Following on the same idea, when a chemical system at equilibrium is stressed, the system works to restore equilibrium. This is Le Chatelier's principle. The stresses are changes to the concentration of either the reactants or products, changes to the pressure, although this is only applicable to gaseous systems, changes to the temperature. Let's examine a hypothetical reversible reaction at equilibrium where reactant A reacts with reactant B to form product C and product D. If we added more A and B, the system becomes stressed and is no longer at equilibrium. To counteract the stress, the system forms more C and D in order to remove the excess A and B. The equilibrium, therefore, shifts to the right. If we added more C and D, the system becomes stressed and is also no longer at equilibrium. So to counteract stress, the system forms more A and B. Therefore, the equilibrium shifts to the left. What happens if we remove C and D as they are being produced, or if the concentration of C and D is decreased? Please pause the lesson to think about this and resume when you are done. The system is now stressed and no longer at equilibrium. To counteract the stress, more C and D are produced, so equilibrium shifts to the right. When concentration increases, equilibrium shifts to the opposite side of the reaction. When concentration decreases, equilibrium shifts to the same side of the reaction. Changes in pressure. The stress to a system at equilibrium is only applicable to gaseous systems. For this stress, we will examine another hypothetical reaction at equilibrium, where reactant A reacts with 2 moles of reactant B to form product C and product D. An increase in pressure means that there is a decrease in volume, so there is less space. Equilibrium will shift to the side of the reaction with fewer moles. In our example, an increase in pressure will cause equilibrium to shift to the right, since there are fewer moles, 2 moles compared to 3 moles on the left. A decrease in pressure means that there is an increase in volume, so there is more space. Equilibrium shifts to the side with more moles, so in our example, equilibrium shifts to the left. So an increase in pressure favors the side with fewer moles, and a decrease in pressure favors the side with more moles. In our next lesson,
Okay, and then notice what our book is saying about how which one has the more gases. Okay, so that's what that's also referring to. Okay, that the more it'll shift to the side with more gases when we're talking about changes in pressure. Okay, let's do an example. A scientist is experimenting with the following. All right, we have NH4, NO2, and we're making NO and H2O. We're looking at all gases here. What will happen to NO and O2? Look at where's NO. NO on the product side and O2 on the reactant side if a chemist adds extra NH4 to the system. So think about it. I'm going to increase the concentration of NH4. Okay, so what is going to happen? It's going to shift which way? It's going to shift to the right, right? The concentration of O2 will decrease because it's going to be used up. The concentration of NO will increase because more of it will be made. So it shifts to the right, to products. Do you get it? All right. Now, I like the idea of the seesaw, right? So I'm adding, some stress to one side of it, and I want to bring that seesaw back into balance. Okay, so let's look at this reaction. CO2 and H2 give me CO and H2O. All gases, good. What happens to CO and H2 if extra water is added? So water is over there on the product side. So if I add more water, what will happen to the reaction? All right, that they will shift toward the reactants. It'll shift to the left because I increase the concentration of one of the products, you see? All right, so more CO2 and H2 will be made, which are the reactants. Okay, what happens to CO2 and water? So CO2 and water if CO is removed. So think about this. If CO is a gas and I have a way of rescuing that gas out, of letting it escape, all right, what can I do? What happens to CO2 and water if CO is removed? Okay, so think about it. Okay, so what do you think is going to happen? Oops, let's see. Hold on. There we go. It's going to shift toward the products and more water will be made. So if I let the CO go, you see, then that is going to release that pressure off of there and it's going to shift toward products. So let's say I'm trying to make water, right? Well, I can do it by bleeding off that CO. All right, next, what happens to CO and H2 if extra CO2 is added? All right, what's going to happen to the H2 and the CO2? Oh, what happens to the CO and the H2 if extra CO2 is added? All right, I'm going to add some more on the left, so that's going to shift it toward the right, right? So CO and water will go up, H2 will go down. All right, does that make sense to you? It's just pretty plain. Think about that seesaw. It's always going to shift, shift, shift to reestablish that balance. Okay, consider CaCO3 a solid, making CaO a solid and CO2 a gas. Okay. Using Le Chatelier, we can force the reaction to completion so that no CaCO3 remains. Okay, if we allow the CO2 to float off, then that would it would decrease in the reaction, right? So CO2 would not be there. That's a stress. So the equilibrium would shift toward the product side until essentially all of the CaCO3 is used up and I have nothing but CaO. If that's what I'm trying to make, then we're in good shape here. And this is the only way we can get this to go to equilibrium, if it lets something bleed off like that. Okay, so the only way for this to get to equilibrium is to have a closed system, like we discussed in the first part of the lecture. Okay, so in order to reach equilibrium with gases, you must have an enclosed vessel. This picture doesn't show it very well, but it's just supposed to be showing how they are in a enclosed, beaker with a top on it right there. It's a bad picture, sorry. Okay, so pressure in Le Chatelier. By changing the pressure on a gas, a stress is introduced. When an equilibrium is subjected to an increase in pressure, it will shift away from the side with the largest number of gas molecules. Now, the video talked about moles, right? So we'll be looking here at the number of gas molecules. So it's essentially the same thing. How many gases and how many of those gases? That's our stoichiometric coefficient, which is our moles. If the pressure decreases, equilibrium will shift toward the side with the largest number of gas molecules, okay? So it'll shift away when it's increased. It'll shift toward all the gases when it's decreased. Okay, if there are no gases in the equation, or if the number of gas molecules is equal on both sides, nothing will happen. When I change pressure, nothing will happen. And we ignore solids and liquids as a stress in this particular deal. Okay, so consider the following reaction. At equilibrium, NH4Cl, a solid, yields NH3, a gas, and HCl, a gas. Okay, so think about pressure. Pressure is going to be increased. So what did it say? What did our little rule say? You probably wrote that down. If not, you need to back up and write that down. So how will it shift? So the pressure's increased. The reaction will shift left toward the reactants because there are 2 molecules of gas on the product side and none on the reactant side. So it's increased, it'll go toward the least number of gases. What will happen if the NH4, if pressure is decreased? Okay, NH4, if it's decreased, the amount of NH4Cl will decrease because a decrease in pressure will cause a shift to the side with the largest number of gas molecules, to the right. So NH4Cl will be used up faster. So it'll make more product. Okay. Which way will the reaction shift if more NH4Cl is added? So think about it. We're just going back to concentration now. If we're going to add more of that, what's going to happen? The solids are added or taken away? No stress. So it's not going to shift. So we add more concentration of the NH4, but it was a solid. All right, and Le Chat will ignore that. Okay, look for those little tricks. Okay, what about temperature? Now, temperature's a little trickier here because we're going to be thinking about temperature as energy. All right, so when the temperature is raised in a reaction, the equilibrium will shift away from the side of the equation that contains energy. This is going to take you back to Module 13 when we talked about thermodynamics. We're going to be looking at the enthalpy here. Okay, so remember our delta H? We have to go all the way back to delta H for this one. So when the temperature is lower, the reaction will shift toward the side that contains energy. So do you remember, so temperature raised and temperature lowered, do you remember how we add energy into our equations? Remember we have exothermic and endothermic? So when they'll give us the delta H on these, and you can insert it into the equation to determine what shift will be. So let's look at an example. All right, so I have H2O, gives me H2 and O2. My delta H is 242 kilojoules. It's a positive number, right? So since it's a positive number, we know something about the energy in this reaction. Okay, so do you remember what it means when I have a positive delta H? It says that my energy is going to go in as a reactant, okay? It's going to go in as a reactant. It is my endothermic, right? So if I increase the temperature, it's like adding more reactant. That's all it's doing. So all we have to remember on this one is that positive delta H is a reactant, negative delta H is a product. And as long as you remember that, then you can say which way is my seesaw being tipped, right? So if we decrease the temperature, it would be like removing a reactant, which would then shift toward the reactants, okay? So, because I'm removing it, right? So it's going to have my seesaw tilting downward on the left side. So I'm gonna shift back toward there. Okay, does that make sense to you? That reminds me, if you end up having some questions over there, you can write those down and email them to me, and I'll get back as soon as I can. We'll see, okay? We'll see if I can answer it. All right. Let's watch Professor Dave explain this to us.
Letelier's principle says that if you induce a stress on a system at equilibrium, the equilibrium will shift so as to relieve that stress. So let's see some examples of a stress we could put on a system at equilibrium. First, we could modify the concentration of any of the compounds. Let's say we add some of this reactant. That will unbalance the equilibrium, and the forward reaction will speed up to use up some of the additional reactants, turn them into products, and restore equilibrium. The equilibrium is said to have shifted right. If we add more products, it would shift left. Likewise, if we selectively remove one of the components, the equilibrium will shift to produce more of that species to restore balance. That is one type of stress we could put on a system. Another stress would be to change the temperature. To see how this would affect an equilibrium, we have to see whether a given reaction is exothermic or endothermic. This tells us whether a reaction absorbs or releases energy and is signified by delta H, the change in enthalpy. If delta H is negative, the reaction is exothermic and releases energy. So we could think of heat energy as a product of this reaction. If instead it's positive, that means it's endothermic, and energy must be absorbed for the reaction to go. So we could think of heat energy as a reactant in that scenario. Once we translate thermochemical data in this way, we can treat the word heat as just another substance involved in the reaction. Higher temperature means more heat, so things will shift to the other side to use up some excess heat and relieve the stress. Cooling it down would have the opposite effect. The third stress we can examine is changing the volume or pressure. Let's say the equilibrium involves gases in a balloon. What if we decrease the volume? If we remember Boyle's law, we know that the pressure will go up. Since the smaller the volume, the more the particles will hit the sides and exert pressure. If there is a discrepancy in the number of moles of particles on either side of the equilibrium, it will shift towards the side with fewer particles so as to alleviate some of the additional pressure. In this equilibrium between a diatomic molecule and two monoatomic species, the right side has twice as many particles. So shifting left means atoms fusing together, resulting in fewer particles, which lowers the pressure on the container. If we increase the volume, thereby lowering the pressure, the equilibrium would shift towards the side with more particles in order to regain some of the lost pressure. Let's check comprehension.
All right, so these are just examples like the ones we have already studied. Okay, sorry for that music right there. All right, so that was just like some of our examples and some of our study guide questions right there. Okay, you can, pause it and take a look at those and see if you were right, that kind of thing. Okay, so let's look here. For the following reaction, I guess, we have a delta H of negative 273 kilojoules, and the reaction has reached equilibrium. And so we see our delta H is a big negative number, so where's it going to go? It's going to go over there on my products. So what will happen to the concentration of each substance, all gases, when the temperature is raised? Okay, so raising the temperature would be like adding something to the product side. So what do you think is going to happen? When temperature is raised, equilibria shifts away from the side that contains the energy. All right, so it's going to shift to the left. Since H is negative, it's exothermic, making the energy a product, so the reaction will shift toward the reactants. HF will go down, H2 and F2 will go up. All right, so I really like the seesaw thing. So just think of it, I've added something to the right, so I'm going to shift to the left. What will happen to the concentrations of each substance if the temperature is lowered? Okay, so we're looking at the opposite right here, yeah? So the equilibrium is going to shift toward the side that contains the energy. All right, because it was lowered, it was taken away from the right side of the equation. Therefore, it tipped to the left, so we're going to tip it back by shifting toward the products. So the reaction will shift toward products. HF will then increase, and H2 and F2 will decrease. Okay? So it's really not difficult. You just think about it, and in your mind, think of that seesaw. Okay. Now, we're going to get into acid bases right here. So this gets a little more complicated. We're just going to add a little kink, a little complication here to it. We know what acids and bases are, right? We know that an acid is one that donates the hydrogen, and the base is the one that steals it. Remember, steals a base. It takes that hydrogen. We're actually talking about something known as pH, which is either percent or particles of hydrogens, is what why the H is big that way. All right, so it turns out if I want this reaction to go, my HCl plus my OH to make H2O plus Cl in the aqueous form, it's a two-step process. We call that mechanism. So it goes step 1 first and then the step 2 afterwards. We've seen that. And so it's going to be something similar to that. We saw that with catalysts, right? How there was mechanism there. Okay, so my HCl is first of all going to separate into my proton, hydrogen without its electron, and the ion of chlorine, which has taken that electron from the hydrogen and therefore is a negative ion, okay? And then that hydrogen will be free to go join up with that OH and make H2O, okay? So we call that the acid ionization reaction, that first step right there, when the hydrogen separates from the acid molecule. So the larger the equilibrium constant, K, all right, the stronger the acid. So when I come up with it for an acid, I call it Ka. And so if I have a high Ka, then I'll have a strong acid. If I have a low Ka, then I will have a weak acid. So you can think of the difference between hydrochloric acid and vinegar, for instance. Okay? And so then you can also see the same thing goes for bases. Remember, bases can be strong and bases can be weak as well. It's just easier to think of acids as being strong. Okay, so the equilibrium constant for an acid ionization reaction is the same as regular K. The concentration of products divided by the concentration of reactants. Okay, we're going to find our Ka that way. All right, let's see. Base is the same for bases, so the products over the reactants. The equilibrium constant is taking those concentrations. And when we find those concentrations, if our Ka or Kb is large, we'll have a strong acid or base. Okay, so what does the ionization constant tell us? The larger it is, that Ka, the stronger the acid or base. So check this out. There's somebody stirring something with a metal spoon. Oh my goodness, look at here, we start over, here we go. That is a strong acid. You probably can't tell, but they're under a hood to do this because it's going to be making some fumes. You see those bubbles coming up? And notice the person is also wearing a glove because it is very, very strong acid. We will not be doing this lab, okay, because you know how I feel about particles going into the air there, okay. But you see how we can have a strong acid, but if they did that with vinegar, it wouldn't have done that, right? So let's look at some of our constants for certain acids. So it turns out, notice over here we have our Ka on the right. Notice for those first four it just says large. So perchloric acid is large, sulfuric acid, hydrochloric acid, nitric acid, those are all large Ka. So those are all strong acids. And then as we move down the list, we can see they're getting weaker and weaker because their Ka is low, it's small. And let's see, where can we get down to acetic acid? See it down there, 1.8 times 10 to the negative 5, very small. That's because we eat it. Right above it, benzoic acid, and above that, formic acid. Formic acid is what fire ants inject into you, fire ants. That's why it hurts, you know, but it's pretty weak, right? Let's see what else. Carbonic acid is what is in your Coke, in your Dr. Pepper. All right, so it's not very strong acid, but it's definitely an acid. Okay, nitrous acid, let's do an example. Nitrous acid, HNO2, has an ionization constant, excuse me, of 4.5 times 10 to the negative 4 molar. Give the equation for this ionization constant. Is this acid stronger or weaker than acetic acid, which has a Ka of 1.8 times 10 to the negative 5 molar? All right, so what are we going to do here? We are going to take what we know, right? And we're going to put it into our Ka, so our products over our reactant, and we are, it says here Ka is slightly larger than the Ka of acetic acid. Oh, because they just gave them to us. 4.5 times 10 to the negative 4 versus 1.8 times 10 to the negative 5. This is a slightly stronger acid than acetic acid. But with that 4.5 times 10 to the negative 4, it's still very small, right? It's weak. So it's just a little stronger than vinegar. Nitrous, maybe that was on our list. Okay, CH3NH2 is a base with a Kb of 4.4 times 10 to the negative 5, so pretty small. What is the equation for its ionization constant? Is it a strong or weak base? Well, with a number like that, yeah, it's going to be a weak base, right? So what am I missing here? Yeah, there we go. My products over my reactants. Notice I've left my liquid one out. And so that's the Kb. It's just asking what's the Kb. Well, there it is. It's that answer right there by Kb is what we're looking for. And then is it strong or weak? Well, it's weak because its Kb, we already know, is 4.4 times 10 to the negative 5. Okay, so not difficult. All right. What is the equation for the acid ionization constant of HF in this particular case? All right, I have HF, which goes to hydrogen and to fluorine, all aqueous. So we're going to see that our equation is going to be our products over our reactants. Is that all it's asking us? Yeah, looks like that's it. Okay, that's easy breezy, right? No problem. Okay, so back to pH. Potential hydrogen, percent hydrogen, however you want to say that. That just remember in pH, the big H right there is referring to hydrogen ion, that's got a positive charge. Okay, so we have a scale that gives us a idea of how strong or weak an acid or base is. Okay, and we know that 7 is considered neutral, and for every unit of change, so 7 down to 6, for instance, is 10 times stronger acid. So it's actually a huge scale. All right, so we have our acids to the left. 0 is the strongest. Our stomach acid's about a 1.2 or so very, very strong. And then our alkaline or base is over to the right, way over there on 13 is like battery. No, battery is an acid, right? So bleach, those kind of things that are over to that side. Lye, those we've used lye in class before. That's a strong base. Okay, so we have weak and strong. Here is an idea of what we can find on those. There it is, our drain cleaner. That drain cleaner that we used last week, I'll have to look at that one. I thought that was an acid, right? Yeah. Okay, but you see our bleach on the right, our soap, our baking soda, all on the side of alkali or basic. Notice water is at 7. Notice blood is slightly basic. Milk is slightly acidic. I'm kind of surprised that a banana is that acidic, right? I could see a tomato and a lemon for sure, and vinegar over there. But an apple and banana, that's interesting. And then, of course, we see hydrochloric acid, the really strong stuff that melts spoons and things, is down there at 0. Now, the stuff in our stomach isn't quite that concentrated. It's like 1.2 or 1.3. Okay, at the back, the last part of your module, it talks about this thing called acid rain. It turns out that all rain is a little bit acidic because there's CO2 in the atmosphere, and CO2 is acidic. But sometimes it can become more acidic based on some pollution in there, namely sulfuric acid that comes from burning certain things in, certain factories, this kind of thing. And then it combines with the H2O to make this sulfuric acid up in the sky. It actually will become part of the rain. So it combines with it to make what is known as acid rain. Now, if it's in a particularly bad spot, here we can see it coming from the factory. It rains down and turns our lakes more acidic, which might indeed kill some fish. It makes our soil more acidic, so it might not allow some plants to grow. Some plants like acid, other plants don't. Notice over here on the right, it's raining down on our trees right there. It can actually affect trees pretty badly. This is a statue that has been subject, it's been outside, and over years has been had acid rain. Look what it's done. The acid has literally eaten away the stone. So that's how strong it can be. It's a pretty old picture. And then here is apparently acid rain on a forest. It doesn't look like a forest fire, so I think it's true there that it's acid that has eaten those away. Now, because mostly that is caused by pollution put out by companies, fortunately, we can regulate them. And so let's see how we've actually helped things get better. Yay, we're going to end on a happy note where things are getting a little better with respect to acid rain.
In 1963, scientists studying Hubbard Brook Experimental Forest in New Hampshire made a shocking discovery. Their most recent rainfall samples were nearly 100 times more acidic than usual. At these levels, additional downpours of acid rain would destroy the region's marine and arboreal ecosystems in a matter of decades. Urgently sharing their findings with fellow researchers, they were determined to answer two questions. What was causing this deadly rainfall, and what could be done to stop it? Rain is never just composed of water. Chemicals and particulates in the atmosphere can be found in every drop, and some compounds, like carbon dioxide, make even regular rainfall slightly acidic. But this pales in comparison to the powerful acids produced when water interacts with oxides of nitrogen or sulfur dioxide. On the pH scale, which measures acidity, each whole number is 10 times more acidic than the one above it. And where normal rain has a pH of roughly 5.4, rain that's interacted with these gases can rank as low as 3.7. Oxides of nitrogen and sulfur dioxide can appear naturally as a short-lived byproduct of volcanic eruptions or lightning strikes. But power plants, refineries, and vehicles that use fossil fuels consistently pump large quantities into the air. These dangerous gases travel with the wind, spreading hundreds of kilometers from the pollution's source. Acting like roaming clouds of destruction, their presence dramatically increases the acidity of local precipitation, creating acid rain, acid snow, and acid fog. These all acidify lakes and streams, kill crops and forests, and damage soil to inhibit future growth. Over time, acid rain can even corrode human structures made of stone or metal. By the 1970s, scientists in North America and Europe classified acid rain as a major environmental threat. But despite clear evidence tying the problem to air pollution, companies denied responsibility and cast doubt on the research. In the United States, corporations lobbied against regulating pollution and convinced politicians that such policies would raise energy costs and threaten jobs. These obstacles led the government to delay changes and mandate further research into the issue. But after a decade of mounting concern, Congress finally took action. Since the bulk of sulfur dioxide emissions came from power plants, the government set a limit on the total amount of it the electric power sector could emit each year. Then, they divided the permitted emissions into a fixed number of allowances distributed to each power plant. A plant could then choose to emit as much sulfur dioxide as they were allowed, or reduce their emissions and sell their unused allowances to other power plants. This system, known as cap and trade, offered power plants the economic flexibility to keep costs low while strictly limiting pollution. Many critics called these allowances licenses to pollute, or said the government was selling clean air. But since the cap was set to lower 5 years into the program, It forced every utility company to reduce emissions in the long term. Some plants added desulfurizing scrubbers to their smokestacks, or switched to low-sulfur coal and natural gas. Oxides of nitrogen emissions were also reduced with relatively low-cost technologies. These advances allowed the power sector to grow while the cap kept pollution under control. By 1985, Canada and the European Union adopted their own solutions, and international treaties began circulating to reduce air pollution worldwide. Today, this science-driven economic policy has largely eliminated acid rain across the United States and Canada. And while many ecosystems still need time to recover, scientists have sped up the restoration of other areas by reintroducing essential organisms killed off by acid rain. Some countries like Russia, India, and China still rely heavily on high sulfur coal and continue to struggle with the environmental consequences. However, acid rain's relatively quick journey from major threat to minor issue is rightly celebrated as a victory for policies that protect the environment. Cap and trade can't solve every environmental problem, but by using scientific consensus to guide policy, adopting efficient technology, and being unafraid to impose reasonable costs for pollution, countries can stop a growing storm of destruction before it's too late.
Okay, so that's good news. So sometimes, government intervention is good, right? It's going to make people be a little more honest, right? I think for the most part, whatever party you belong to, everybody wants clean water, right? Nobody wants dirty water. I mean, you think about these companies that are producing these pollutants, so it really, putting pressure on them to scrub them and things like that is a good thing. And so I think it kind of ends on a little positive note there. Okay, so that's it for our lecture, y'all. I really feel like I'll be fine because I think I just have a regular old cold. And I just didn't want to chance it with you. Okay, so watch this and then let me know if you have any questions. And next week we will have a quiz over it, okay? And we'll do our little lab that goes with this, okay? If we have questions, we can actually put this back on next week and go through some of the things. All right, gang. See you soon.